Good afternoon. It's Mrs. Allison, and today we are going to talk about derivatives of inverses. Before we actually begin, I would like you to try a warm-up problem. So go ahead and hit pause and try the problem and then come back when you've got it. All right, for this problem, what I would do first is look at, and I'm going to shorten this just a little bit. We know what it says, so I'm going to keep going. Oops. And maybe we look at it just a little bit differently. Maybe we see this, so let's go back to the pen, as 1 over n, and the square root of 1 over n, and the square root of 2 over n, because we see that being a pattern. So maybe that does clue us in as to our formula just a little bit, looking at it this way. Maybe we can then rewrite this as the sum from I equals 1. We'll call this our first term. We'll assume this is our first term, then second term, all the way to the nth term. And when we look at the nth term, we may say, okay, based off of that, each time I'm taking 1 over n and multiplying it by the square root of I over n. Okay, so looking at it this way, we may get that equation. Now, there's other ways to come up with that, but that way seems to make the most sense to me. Now, if you remember your Riemann sums, we know that this f of a plus delta x I is the formula that we started with to be able to write the sum in summation notation or in sigma notation. And when we look at this way, what I've got is that my a term in this case would be 0, and my delta x term here, my change in x term, would be 1 over n. And so I can rewrite this to be the function evaluated 0 plus 1 over n I. Or we might say f of I over n. Okay, well, looking at that, how then do I get to where I'm going? Well, I know the number of terms based off of how many I think are there, counting at the top numbers. If we look at those top numbers, I'm going to assume that there are 20 terms because it ends at 20 over 20. So I might then even rewrite this f to be the function of I over 20. Okay, well, if it's the function of I over 20, then my function that I'm plugging in each time, the function that I'm dealing with, is going to be the square root of x. Because each time I'm taking I over 20 into the function, and each of these functions is the square root, and then I'm plugging in an I over 20, I over 20, I over 20, for up to all the number of terms. Okay, so using that as a guide, I can eliminate problem A. I can eliminate C, but then that leaves me with 2 that I'm not quite sure about. Well, I need to then look at my bounds, and my bounds of integration that I'm going to talk about are going to rule out problem E, or letter E, because if we look at problem E, or letter E, we get delta x equals 20 minus 0 over n. Remember, our delta x equals the b minus a over the number of rectangles. And so for us in this problem, this delta x would need to be 20 over n. And 20 over n is not going to give me what I want for this Riemann sum. And so therefore, the answer that I would choose is going to be B to give me that Riemann sum. let's move on to the idea of inverses, or the derivatives of inverses. And just let's bring up some things that we've talked about in the past about inverses. Remember that inverse functions, the graph of f, if we have any graph of f, its inverse will be a mirror image across the line y equals x. We also know that the domain of f of x will be the range of the inverse, and the range of f of x will be the domain of the inverse. So essentially, we can take any point, a, b, in my original function, and it will become the point b, a in my inverse function. Okay, so what we're going to try to look at now is the relationship of the derivatives of the inverse. And if we were to draw the slope of the tangent at these points, meaning if we were to draw the slope right here, and I'm going to pretend to try to draw it straight, it's close, and we were to draw the tangent of this point here, still off a little bit, what would we be able to say about those? Think about how we might relate those two lines if I were to have drawn them straight. Maybe you can draw them with a ruler. Well, let's see if we can't find some conclusions by looking at inverses maybe with a concrete example. Okay, so I would like you to start by graphing the square root of x, then find the inverse, then sketch a graph in the coordinate plane, then differentiate both, find the slope of both, and draw a conclusion. So take a second, hit pause, and walk through this example. All right, and going through this example, here's what I've got. F of x equals the square root of x. Let's do that better. F of x equals the square root of x. So we'll graph this one in blue. If I graph the square root of x, the square root of x has points at 0, 0, 1, 1, 4, 2, and it looks like half a parabola turned on its side. Now to find the inverse, this may take you back just a little bit, but to find the inverse, and we'll do this one in red, to find the inverse, what we're going to do is we are going to switch our x and our y. So my function is y equals the square root of x. So we're going to switch the x and the y. So x equals the square root of y, which means x squared equals y, or the inverse. I'm going to write inverse notation there. But the problem is, if we looked at x squared is a parabola that looks like this, and that would not be the inverse. So I need to restrict my domain. So I'm going to be particular about this one, and I'm going to say that the inverse, we'll put it back in the function notation, is going to be x squared as long as x is greater than or equal to 0. So let's sketch a graph of x squared. Okay, so this is my inverse function in red. And you can see that it fits the pattern that we talked about on the previous page, that they're mirror images of each other across the line y equals x. The domain of one is the range of the other. We can see that. Now, if we want to differentiate both, if I take f of x, which we know is the square root of x, and I take the derivative of this, we get 1 over 2 root x. And if I take the derivative of the inverse, so I'm going to write it like that, a little weird. Before I do that, let's actually just write the inverse is x squared. So if I take the derivative of this, we get 2x. Okay. Now it says, let's find the slope of the graph of f of x. So remember, f of x was in blue, so let's find the slope of the graph of f of x at 4, 2. Well, to find the slope, we're going to use that point at the derivative. So the derivative of if f of x is root x, f prime of 4, the slope at 4 is 1/4. The slope of 4 is 1/4. And if we do that in reverse for f of x, the inverse function we know is x squared when x is greater than or equal to 0. but the derivative or the slope at the point 2, 4, this should have been a 2. The slope at that point, when I plug that in, I get 4. So then the question is, what conclusion can we draw about these slopes? What we notice about these slopes is, or what you should notice about these slopes, is that they're reciprocals of one another. Remember, reciprocal is a flip of the fraction. So before we try to make sense of this with derivatives, let's look at what a table of values might look like, because I think this might help in getting our thoughts going just a little bit. So we know that if we have a table of values where x is 3, 1, and -1, and the value of f of x at those points and g of x at those points is given, then to make a table of values for the inverse of f, all that we're going to do is we're going to switch the x and the y. So for example, x here would be 2, and the inverse of f at that point would be 3. -1, 1, 4, -1. And the same thing with the inverse of g. We would have -1, 3, 0, 1, and 3, -1. In both of these cases, you'll notice that the domain from my original function, 3, 1, -1, becomes the range of my inverse function. Okay, keep this in mind, because as we start to look at finding the derivative of the inverse, this will help. So to find the derivative of an inverse, we're going to start with the composition of f and its inverse. And hopefully you remember this from algebra, probably 2 at that point. Algebra 2. That if we take f of the inverse of x, if they're going to be inverses of one another, when we do that, we get x, a value of x. And you know what I'm going to do is I'm going to rewrite this in a different color. So if we now take the derivative of this, so let's go and take the derivative with respect to x of this composition. In doing that, we would need the chain rule, right? So using the chain rule, what we would get is we would get the derivative of the big outside function, and what would be inside is still that inverse, multiplied by the derivative of the inverse. So the inverse's derivative, I'm going to notate that like this, equals, and then the derivative of x would be 1. So here's what that looks like when we use the chain rule. Now remember, our job is to find the derivative of the inverse. So to find the derivative of the inverse, what we're looking for is we're trying to solve for this portion, the derivative of the inverse, and get it by itself. So we would get that the derivative of the inverse, so when I have the inverse function and the derivative of that, it's going to equal 1 over the derivative of the function evaluated at the inverse. So using what we just found, we can say a couple things. One, if we have a point AB, and that is on the function, and the point BA is on the inverse, what that means is that the derivative of the inverse evaluated at B is equal to 1 over the derivative of the function evaluated at A. Or, if they're inverses, then the derivative of G is equal to 1 over the derivative of F evaluated at G. That's if F and G are inverses. So what we know, what we've seen so far, is that derivatives of inverse have reciprocal slopes. Their image points are reflected across the line y equals x. So AB becomes BA. We've seen all of this. So now let's try to put this into practice with finding derivatives of inverses. Let's start with this first example. This asks us to find g prime of negative 1, where g is the inverse of f of x. Okay, g is the inverse of f of x. All right, so let's look at some notation. If g is the inverse of f of x, then g of x, we have the ordered pair negative 1, 3. That's because in f of x, we have the point 3, negative 1. Okay, so if we are asked to find the derivative of g at negative 1, it's going to be equal to 1 over the derivative of f at 3. And since we have the table of values, the derivative of f at 3 is negative 4, and so then this would be 1 over negative 4, or negative 1/4. Let's look at another example. So again, let f and g be inverse functions, and then it breaks down this table of values. Essentially, it's the same as the table that we were given up above, just in a different notation. So if it would help you to visualize, if you're a visual person and you want to see this written a little bit differently, maybe you set this up as x, f of x, and the derivative of f of x. So then we'd have negative 1, 1 was a point, 0, 2 was a point, and then 1, 5 was a point. And then the the derivatives at each of those were 3/2, 2, and 1/2. Okay, so either way, I don't care which you use. Now what they did say is g is an inverse function of f. We were given f, so we're going to use f as our primary function and then g as our inverse function. So let's look at some of these. Let's start with g of 1, g prime of 1. Remember, g is the inverse of f. So f inverse equals g. They're the same. Okay, so if we see g prime of 1, really what I need to do is 1 over f prime of negative 1. The reason I need to use f prime of negative 1 is because the inverse point, negative 1, 1, if I'm trying to find g of 1, I know that the inverse of that would be 1, negative 1. That would be the point. So what I'm going to do now is I'm going to do 1 over 3/2, or we get 2/3. I don't have room right there. So my inverse of the derivative is 2/3. So hit pause and try B. See if you can get it. Okay, hopefully looking at this one, you can mimic what we did in A. G prime of 2. 2, when we're talking about the inverse, the point I have in F is 0, 2, so that means the point in G is 2, 0. So G prime of 2 is 1 over F prime of 0. And 1 over F prime of 0, well, F prime of 0 says that F prime of 0 is 2, so my answer would be 1/2. Okay, hit pause and try C. Okay, so this one gives us G prime of 3. Anybody have any luck? There isn't a G prime of 3. We don't have any value for G of 3. We don't know anything. Remember, we'd be looking for the range of F would be the domain of G. So the domain of G being 3 should mean it's in the range of F. And since we don't know that, we don't know enough about these functions, this is not even possible. It's not possible to find the derivative of G at 3 because we don't know any range values for F at 3. Similarly, what about part D? It is not possible either. It's not possible either because there is no range value for G that is 0. Yes, we have a domain of F that's 0, but we don't have a domain of G. I just said range of G. I meant domain of G. We don't have a domain value of G that is 0. Okay, so hit pause, try part E. Looking at part E, we have g prime of 5 equals 1 over f prime of 1. That we have. And f prime of 1 is 1/2, so we get 1 over 1/2, and so this would be 2. So g prime of 5 is 2. Okay, let's look at an example where we are given a function and we are asked to find an inverse. So in this example, it says, let g be the inverse of f, and we want to calculate g prime of -9 for the function f of x equals 4x cubed plus 5x. Okay, so using the formula that we have found, we would say that g prime of a equals 1 over f prime of b. Okay, keeping in mind that g of x being the inverse, if we're looking for -9 here, then in f of x, what we've got is we know the range has to be -9. Keep in mind, those have to be the same values. These two values that we're going to work to find are actually the same values, right? That's what an inverse says. So since we already know what f of x is, let's set up this equation. Let's set up the equation -9, the y value for f of x, equals 4x cubed plus 5x. So I can solve for x to get in f of x to get the y in g of x. Okay, and in solving for this, I would probably just plug this into my calculator. I'm guessing it could be factored through other methods, whether it be synthetic division or maybe even grouping somehow. I would just probably plug this into my calculator to get the x value. So plugging this into my calculator, if I let -9 equal one of my y equals and 4x cubed plus 5x equal my other one, what I'm going to see is that x equals -1. Okay, so what that means then is that g of x has the ordered pair -9, -1, whereas f of x has the ordered pair -1, -9. Now, when I go to find the inverse, or the derivative of the inverse, g prime of -9, what I'm going to get is 1 over f prime of -1. And f prime of -1. Well, now I would actually need to do a little bit of math for that. So f prime of -1, well, we know f of x equals 4x cubed plus 5x. So f prime is 12x squared plus 5. And if I plug in -1, I would get 12 plus 5, or 17. So g prime of -9 is 1 over 17. How'd you do? All right, now I am going to show you one more way to solve this that we could have done, although I think you're going to see that maybe this method is a little bit simpler, at least the basics of the math are a little bit simpler. We know that inverses, if I have the function f of x equals 4x cubed plus 5x, then g of x is when I get x equals 4y cubed plus 5y. And if I wanted to find g prime of x, I'm going to take the derivative implicitly here, kind of. Just take it a little bit, it'll look a little bit different. The derivative with respect to x of this function, and we're going to do the function x equals 4y cubed plus 5y. And I take the derivative of this. We're going to get, with respect to x, we get 1 equals 12y squared plus 5. I need the dy dx because I took this implicitly. And so solving for this, I know that the derivative of y with respect to x of my inverse function, because g was my inverse function, is equal to 1 over 12y squared plus 5. Now, I would need to evaluate this at a point, but the point that I would need to evaluate it at, I would have had to go through and find like we did up here. So I would need to know that the point that I'm solving for is this point right here. And so after solving for that point, then I could take and evaluate this function when y equals -1, and we would get 1 over 17. So it would be the same derivative of that inverse function. It would just take a little bit of a few more steps to get through. It's just another way to look at it. And I'm okay if you use whichever method makes the most sense to you. So tonight you have a circuit training on inverses. We don't have anything new on Friday, so we will go over that on, we can answer questions on Friday, but go over it next week. Have a great day, and we will talk to you soon.